So I'm going to talk to you a little bit today about machine learning in neuroscience, more at kind of a fundamental conceptual level, not particular code examples with this presentation. So for those of you that don't know me, I did my undergraduate master's here in Rasmus Peterson's lab, and I was mainly focusing on machine learning, predictive models, behavioral analysis, and in vivo electrophysiology. I created the first whisker tracking method in freely moving mice, which was used in our publication this year in Current Biology. And we'll go through that a little bit later as well. At the moment, I'm a BBSRC-funded PhD student in Rob Wykes' lab, and I'm looking at developing wireless biocompatible brain implants for mice to try and study the relationship between infraslow oscillations, circadian dynamics, and hippocampal activity. So what I want you to kind of get out of this session, I want you to understand the conceptual flow of a machine learning pipeline for analysis, be able to describe the difference between supervised and unsupervised learning, gain a geometric intuition for machine learning, and grasp how model performance is quantified and validated, understand the fundamentals of XGBoost and regression techniques, and then further understanding how those are applied to particular neuroscience examples. So we'll start very, very basically. Fundamentally, what is machine learning? Machine learning is the process of this equation, which is where you have some input, pass through some process to produce an output. And your inputs could be something like neural activity or financial data or biomarkers, and we can get things out of it, such as internal speech from that neural data, or perhaps a risk analysis on your stock options, or cancer detection, or malignancy or not. And depending on the flavors of your data, the particular data structures and what you want to get out of those data is what dictates the process, the arrow, whether it's regression or decision trees or neural networks. And that's where machine learning is difficult. It's understanding the particular relationships between data structures and architecture structures and picking the one that's best suited for your particular problem. But the overarching structure of machine learning is quite simple. So broadly speaking, we have to separate it now into two categories of supervised and unsupervised learning. Where supervised is the X to Y structure that we mentioned, where we have labeled data. So there is wrong and right answers, which we can use to reinforce and correct our model and drive it towards minimizing residuals, minimizing errors, and becoming more accurate over time. Tasks like regression and classification. Whereas unsupervised learning is where we don't have predefined assumptions about the data or right or wrong answers. We're not driving the model to minimize errors. We're trying to uncover hidden patterns in the data set. We're not really going to talk about unsupervised learning. I'm going to very much focus on supervised learning techniques for this talk. So supervised learning is the process of discovering some function f that maps inputs x to some outputs y, like we just covered. And it can be said a little bit more elegantly like this, where y is equal to f of x plus errors. Because real world data is noisy, your mathematical relationship that you define is never going to exactly predict your output data. And examples of that could be if we have some input data on the x-axis and we're trying to predict the y-axis and there's a parabolic function, machine learning is finding the red line here. It's finding the function that describes the relationship. Or we could have points in 3D space and we need to define some geometric decision boundaries that will classify them into groups. But that's kind of the crux of what I want to get across to you today, is that machine learning isn't arbitrary statistics on paper, it's geometric exploration of data. And when that penny drops, everything else becomes a little bit easier. So, did not mean to go there. So the first thing we need to kind of address is the difference between test and training data and what the point of splitting them is. So the typical kind of baseline approach for any machine learning model is to train your model on 80% of the data and then test it on 20. And you want to do that because you don't want the model to learn the relationships in the data. Sorry, you don't want the model to memorize the data. You want it to learn the relationships between your inputs and outputs. And so if you test your model, you look at your model's accuracy on its training data. If it's high on the training data, but then can't predict your test data, you have an overfit model. If it's low in both, then it's an underfit model. It's just not very good. And high on both is what you're aiming for, a good generalized model. So it looks a bit something like this. If we define some exponential relationship, we take 20% of those data points and we remove them, and then we fit our model. So if we just fit the mean, which is the dumbest possible model that you can have, measure the mean squared errors, the distance between the predictor and the actual points, it's pretty poor for both test and train. We have a bad model, it's underfit. If we use a high order polynomial and really capture all of the data points to minimize the mean squared error to 0, when we look at the training data, the test data, it's not very good. And then if we have a nice generalized approach, we get similar generalized scores for the mean squared error between the test and the train data. And that's what we're looking for. So we're looking for generalized models that learn the relationship, not their particular data set. So I'm going to introduce you to a particular, so that's the kind of general overarching idea of overfitting and underfitting. But I told you that machine learning is the process of finding the function f of x, finding the arrow in the x to y. So I'm going to introduce you to one of those techniques called XGBoost regression, and it'll become apparent why I'm introducing you to this particular one. So it's a gradient boosting regression model that uses an ensemble decision tree. But what does that even mean? It means it uses loads of little decision trees to work together to reduce the errors of the previous trees. And I've got a visual example so it's less arbitrary. So let's say we're trying to predict house prices, and we have our input data as house A, B, and C, all of the prices recorded, and we know their actual values. What XGBoost will do is it will initialize and guess. So it will ask a question about the size of the house and bin it to a random value. The second tree, the point of it is try and predict how wrong the first guess was. So it'll ask another question like, does the house have a pool? If yes, put it into one bin where the bin is the prediction of the house price, or no, the other one. And then it's not trying to guess the price now, it's trying to guess how wrong the previous tree was. And when you stack this over time, and over lots and lots of trees, you converge towards the correct answer. You're minimizing the errors by predicting them and then subtracting them. But I just said to you that machine learning is the geometric exploration of data, and this feels quite arbitrary. It doesn't feel very geometric. I spent a very, very long time making it geometric for you. So let's say our problem now consists of square footage of your house and how many rooms it has. And we take these on the x and y axis. And then the vertical axis is the price. We can define some relationship in 3 dimensions and fit a linear plane to it, which would be a linear regression model. So the combination of these 2 base vectors tells us how high to go on this plane, and then we read that off, that's the price. That's what the model is, it's a flat plane. What XGBoost does is it produces a prediction surface. So this is actually an XGBoost model predicting these data points. And instead, we're asking how the combinations, it's a non-linear relationship, and we're predicting from this surface rather than a flat plane. And that's the kind of geometric jump in XGBoost. But why am I even telling you about XGBoost? Well, it's because it's what we used in this paper that we published this year, which was, we found encoding of body state in whisker-related somatosensory cortex of freely moving mice. So I'm going to give you a bit of background and understanding as to what the problem is and why we bothered to look into it. So in 1909, the areas of the brain were devised based on cellular cytoarchitecture by Brodmann. So he looked down his microscope, cut the brain up, and noticed area-based differences in the cellular architectures and defined them. And then in 1937, Dr. Penfield, who was a surgeon working on epilepsy patients, took a charge probe and would go around and poke M1 and S1, so precentral, postcentral gyrus, motor cortex, and somatosensory cortex, and note the responses, quite literally, with a little stick, and he put little paper tags on them and built up an idea of what the functional representation of this cortical area is. And then we kind of get more of an idea of what these cortices are doing. We find the delineation between visual or auditory cortex or somatosensory cortex. And then we get really high definition kind of understanding of this bottom-up sensory view of processing. So in 1959, Hubel and Wiesel classified the cat visual system under anesthesia. And we thought that was kind of the whole picture, where your input will go through the retina, pass through the thalamus, and then to the higher cortical areas to sequentially process different features. And we're like, that's it, that's how vision works. But in 2010, Neil and Stryker kind of shifted the paradigm with their research. So they did a head-fixed investigation where the mouse has its head fixed. They're recording from visual cortex, and the mouse is atop a floating styrofoam ball that acts as a treadmill. And they found that locomotion in and of itself actually modulates the neurons in V1, which is not something that we expected if we considered the visual cortex to be purely processing visual information. Why is locomotion causing a difference? If the mouse was running in an open field, maybe it's the difference in visual flow versus stationary and running, which is causing the difference. But we can say that's not the case because it's head fixed. So its field of view, it's the input to its visual system isn't changing. The actual locomotion in and of itself is altering how these neurons are firing. So that was pretty interesting, and it sparked a whole range of research around this problem. But we chimed in and thought, if we're seeing behavioral representations in these sensory cortices, but we're head fixing the animal, we're very, very much restricting the behavioral paradigm, its behavioral repertoire that it can produce. So if we want to understand this effect more clearly, we need to do it in a freely moving scenario, but that's quite challenging. So instead of using vision, we moved over to the whisker system. So a little bit about the whisker system. On the left here, this is the cortical representation of the whisker system, which is organized into structures called barrels. So quite literally on the surface of the mouse cortex, there's these cylindrical shapes that travel down perpendicular to the cortex surface that represent particular whiskers. So for example, this barrel is processing this whisker in somatosensory cortex, and vice versa. So there's a one-to-one mapping of whisker to cortex. And unlike with vision, if we can somehow capture the kinematics of whisking behaviors, we for sure know the input to that system. Because if we look at it from the perspective of the visual system, it's almost impossible to track and ensure you're aware of the exact pattern of light falling on the retina at any given time. Because if the mouse is moving around and even just saccades its eye slightly, the input to your system is now completely different. You can't determine it. Whereas with the whisker system, if you can track whiskers, you know for sure the input to this system, what this barrel is processing, is the exact shear force acting on this whisker. So if we can track that whisker, we know what is going into it and therefore can try and understand the computations that are happening. So how do we do that? Well, Joaquin and I from Rasmus's lab built this. This is my behavior rig, well, our behavior rig. And at the top, you will notice a big fat infrared panel, followed by 4 cameras around the top looking into the arena, the actual behavior arena itself, and then a high-speed whisker camera underneath. And then moving into the arena, you'll see the mouse exiting the holding chamber at the front and approaching an object of interest. And in its head, it has a NeuroPixel 2.0, which is one of the best kind of eFIS devices that we have at the moment. 5,120 channels, 4 shanks, so we can record across the structure and through the structure as well. And we're recording from barrel cortex, but we also are doing investigations into whisker-related thalamus as well. But moving up, we have the 4 body cameras that I mentioned. Excuse me. And what they're doing is they're capturing different reference frames of the mouse, and they're applying this residual neural network, which is a tracking software called DeepLab Cut, which allows us to track key points over time on the mouse. We also do some high-dimensional unsupervised learning techniques to pull out the principal components of behavior, but it is quite complicated, and I'm not going to get into that too much now. Read the paper. So moving underneath to the high-speed camera, what you may have already noticed is that the floor of this arena is actually transparent. You can see the little mouse's head poking through here. But from the perspective of the camera, you're looking directly up at the object with a perfect backdrop of the infrared light, which looks a bit something like this. Now, in this example, the pole, this object is stationary and the mouse is moving, but I developed a technique called virtual head fixation, where we have a frame-wise correction to the head orientation such that we can then track the whiskers as the angle between the x-axis and the actual tracked whisker as well. So that's it, we have high-fidelity whisker information, nice. What about those body cameras? Well, we have those 4 synchronized views of the mouse at any given time with the DeepLab Cut working to track predefined body points. And because we have this synchronized view from multiple angles, we have a predefined matrix that we can compare it to with some linear algebra, and then we get a 3D reconstruction of the mouse in space. Nice. So for our predictive models, we have single unit spike trains from WS1, barrel cortex. So we have single unit fidelity. It's not like a summative electrical activity of multiple neurons, literally individual neuron spike trains. Body state information in the form of high-dimensional representations, but just think of it as a kind of mathematical description of the mouse's pose in 3D space, and derivatives of, and then we have the whisker angle. So kind of linking it back to the beginning, how are we using this supervised learning approach and why are we doing it? Well, we find that when we try to predict spike trains from whisker kinematics, we actually achieve a max R squared of 0.46, a 64% variance explained. What's R squared, I hear you asking? Well, R squared is if we take a spike count over time and we just use the mean to try and predict that spike count, we get an R squared of 0. And as we approach a perfect prediction, that gives us an R squared of 1. So it's a value between 0 and 1 that kind of compares your model from perfect prediction to the dumbest possible prediction. So an R squared of 0.64 means that we're explaining 64% of this data from the whisker kinematics, which does make sense because we're recording from the whisker-related part of the cortex, and the input information to our model is the angle of those whiskers over time. But the interesting thing that we find is that when we actually have these whisker kinematics with body state information, the median explanatory power of each neuron increases by 68%. So the body state information is being represented alongside the whisker information. Just to kind of clarify with this, some people might go, okay, but what if your body state information is actually capturing correlates like gravity-related stuff on the whiskers? So as the mouse is moving, the whiskers are going to be bouncing up and down. Maybe that's what's causing the increase in explanatory power. Short answer is no. We did a control, which is an infraorbital nerve cut. So you cut the nerve that supplies the information to the cortex from the whiskers. And in the absence of any whisker input, we can still predict activity in barrel cortex with fairly high R squared.
I just need to say that I did a presentation on your paper 2 weeks ago.
No way, really?
Yes.
No way. Awesome, very cool.
For Ricardo Storky, do you know him?
Yeah, I do. Oh, awesome, very cool, very, very cool.
Yeah.
But I want to kind of go over a different concept, which is when you're trying to analyze data, we don't use train test split, we use something called k-fold if you're trying to validate predictions and not use it to make future predictions. So if we just do the train test split and we split this 20% here, we get a really nice R squared. But if we move where that split is across the time series data, we're going to get different R squared values. So how do we kind of validate our actual predictive power across the entire data set without removing any of it? Well, we use a k-fold cross-validation technique where we essentially take this bit and test on this bit, train on the rest, test on this bit, train on the rest, test on this bit, train on the rest, and we do it for all of them. And then we get 5 predictive models across the data set so that every single piece of data has been trained on and tested on independently. And then we take the summative values of these R squared results, and then we get an R squared for the entire data set. Not 0.74, that's just an example. We got 0.64, but still. So kind of overall, I hope that's kind of given you a bit of insight into how we used supervised machine learning in our most recent paper, a bit of a geometric intuition about how supervised machine learning techniques make predictions, the idea of training data and testing data, and the most appropriate methods depending on your intended goals, introductions to regression, and then most importantly, the body state is encoded in Whisker S1. So I would very, very, very highly recommend that if you're intending to kind of move into doing neural analysis with machine learning, that you look into the unsupervised methods as well, like dimensionality reduction techniques like principal component analysis, or clustering techniques like k-means, and t-SNE for nonlinear, and neuron clustering as well, so looking at neuron firing properties and clustering them into particular cell types. 3 Blue 1 Brown on YouTube inspired everything I do presentation-wise, and read our paper if you want to know a bit more. It's actually quite cool. So yeah, acknowledge everybody on this paper for giving me such a great time in my master's, and thank you very much. Any questions?
We'll just start the recording and then you can ask some questions, if that's okay. I already have some questions, I have to say.